So, in this session of waves in space-time and propagation, we are recapitulating the geometrical aspects of the wave propagation in space-time. In the earlier slide, we have deliberated on the transformation properties of the fields under these two discrete transformations that we have defined by time reversal transformation and space inversion transformation. But it is not that these two transformations, they only affect the active variables, they also do affect on the inert objects like the complex number square root of minus I or the Levy beta symbol epsilon, mu, nu, lambda, sigma, or the coordinates themselves. So, how do we in general assign the transformation law to these objects under parity, time reversal, or charge conservation? They are usually done by looking at the associated objects where they appear. So, let us take for example, if you are looking at a conservative system, that is energy conservation is implied, then whether we go forward in time or we go backward in time, the energy should not change. They should remain the same. In a wave or for a wave, this is realized by putting either e to the power I omega t when we are moving in the forward direction, or we are moving in the backward direction, e to the power minus I omega t. Now, this omega is what is related to the Hamiltonian of the system, and the Hamiltonian for a conservative system is a Hermitian operator, and the omega or k naught or 0th component of the wave vector is related to the temporal component of the space-time variables. So, if the temporal component of the space-time variable reverses its sign under time reversal, then to maintain that the Hamiltonian or k naught should not change demands that this quantity or this object I should change its sign under time reversal operation. So, that is how the transformation property of this quantity I is actually fixed. However, if we look at the spatial components, that is to say, let's say x or y or z, they do not enter into this description anymore, because time translation invariance is what leads to the appearance of constant energy. but not with the other three that we have mentioned. So, under space reversal transformation, I retains its sign, and the same thing remains true under charge conjugation. I mean, here the idea is also same as before. By charge conjugation, if we start with a system ensemble of positively charged objects, and we suddenly change their charge to some opposite charge, then naively speaking, they are antiparticles of each other. So, their mass should not change. Therefore, or rest mass should not change. Therefore, the energy in general should not change, and the interaction among them when they were positively charged, whatever interaction energy was there should be the same when their charges have reversed, if the system is inert under the charge conjugation. So, I does not change under charge conjugation. So, we can now move on to other objects, and the object or objects, those can be considered here are: one is the metric tensor, and the other one is the totally antisymmetric Levi-Civita tensor, defined in terms of epsilon, mu, nu, lambda and rho. The metric tensor G mu nu in general is a diagonal matrix with off diagonal terms equal to 0, and one can multiply this matrix from left by time reversal matrix T, and from the right by T inverse, to establish its transformation law under time reversal, and same for space reversal, and under charge conjugation, it is our common sense that there is no change in the flat space-time metric, whether you are talking of particles or their charge conjugated version. Those are antiparticles in general. So, the metric tensor remains inert. However, the tensor of rank 4, the Levi-Civita symbol does not remain inert under both the coordinate inversion transformations. However, under charge conjugation, it does. Nothing happens to it. A naive guiding principle to track this fact lies in realizing that this Levi-Civita symbol is 0 in the first place when any two of the indices are same, and that immediately brings out the conclusion that each index of the Levi-Civita symbol must be different. So, to begin with, if we start the first symbol to be 0 or first index to be 0, then the rest of the three should have spatial indices. First one has temporal indices and the rest of the three has spatial indices. So, on the time reversal it is supposed to change, and similarly under space reversal this is also supposed to change. So, we land up with the condition that if we operate T from left on the Levi-Civita symbol and T inverse from right simultaneously, it should have picked up, or it would pick up a negative sign. Now, a Levi-Civita symbol with all indices up is equivalent to the same with the negative sign with all indices down. So, what we get is relation number 49, that under time reversal operation, all the up indices of the Levi-Civita symbol actually goes down. And if it happens for the time reversal matrix or T operation, then it should also happen for the parity operation. So, we get the transformation rule for 49 and 50 to be the same, and you can guess that you can keep the Levi-Civita symbol same if we operate from left and right by PT. The third relation is the behavior under charge conjugation. Charge conjugation is independent of any coordinate change or coordinate transformation. So, under charge conjugation, this particular object retains its original form. To put it differently, one can say that under a duality transformation, the net charge associated with a system does not change, it remains the same. Therefore, under charge conjugation, the Levi-Civita symbol remains its original form. Now, having talked about these two objects, those neither depend on coordinate nor on charge, but still changes their character. We have now other objects before us whose transformation laws need to be assigned under the discrete transformations. We already have seen that under continuous transformation, Lorentz transformation, they do not remain the same, they undergo changes. But here we are now looking into discrete transformations and their behavior under the discrete transformations. So, to begin with, let us say that we have a 4 coordinates of a space-time vector. The 0th component is a temporal component and the 3 spatial components. So, by definition, change in time should be related to the time reversal transformations. So, no wonder what we get is for a contravariant tensor, time picks up a negative sign and the spatial coordinate remains the same. Now, if you take a negative sign common or you multiply this whole set by a -1, then your t becomes positive, but x becomes negative, and that is the definition of your covariant tensor. So, as a result, under temporal inversion, a contravariant tensor becomes a covariant tensor with a negative sign. And since these operations are 1 to 1, so if you make the covariant vectors undergo this transformation, we will get back a contravariant tensor with a negative sign. This is about the temporal inversion operation. So, what about parity transformation? Please recall that under parity, the spatial coordinates change their sign. So, under parity, a contravariant tensor will have its spatial coordinate with a negative sign and a vector with spatial coordinates negative is equal to the covariant vector. So, under the operation of parity transformation, a contravariant vector goes to a covariant vector. And the last one is charge conjugation. I mean, it is a very well known established experience that if we translate an object in space, then its net charge does not change, or in other words, if we have a or if I have a charged object located at some position in space, then under charge conjugation, you have a charged object somewhere in space. I just change its charge from positive to negative, and this operation does not give me the change in the position of this charge, it remains where it is. So, under charge conjugation, there is no change in the coordinate x. So, we have discussed three kinds of transformations so far: on the complex quantities, on the tensor of fourth rank or antisymmetric tensor of fourth rank, when the antisymmetry is against the interchange of any two indices, and third one is the coordinate and their transformations. What is left is a wave vector that usually is represented by k mu, and it is related to its counterpart in the dual space or Fourier space by I del mu. So, if we take a transformation, that is time reversal transformation, then under time reversal transformation in one space should not modify the form of the time reversal transformation in the other space. That demand is slightly superfluous. But what is very strong is, if we concentrate on a particular space, let us say the four-dimensional coordinate space we concentrate on, we apply the time reversal transformation on this, then according to the established transformation rules, what happens is the parts associated with temporal coordinates get a negative sign, the associated factor of I gets a negative sign, and as a result what we get is the overall, the spatial parts picks up a sign, but the temporal parts and the factor of I does not pick up a sign, which is the third term on the last line after equal to sign. Well, there are two equal to signs and this is the third one. And this particular object is equivalent to a covariant derivative. So, the contravariant k wave vector under time reversal transformation is equivalent to a covariant wave vector, and that's it. This fixes the time reversal invariance transformation of the wave vector. There are two more transformations we are left with as far as the wave vector k mu is concerned, and they are under parity and charge conjugation. Under parity, the argument goes almost parallel to the one what we have given provided so far for the temporal one. So, under parity transformation, the contravariant vector becomes a covariant wave vector. I did not say the word contravariant wave vector, but let me add it. The contravariant wave vector becomes a covariant wave vector, and under charge conjugation nothing happens to k remains inert. So, the contravariant wave vector remains a contravariant wave vector. If we compare them vis-a-vis their counterpart in the Cartesian coordinate system, what we see is there is a departure in the transformation law of k mu and x mu against temporal transformations. The x mu picks up a negative sign where k mu and becomes a covariant vector, but k mu does not. Under parity, they almost transform similarly, and under charge conjugation they are the same, the form is same. Okay. So, that brings us close to the description that a wave equation usually needs to describe its propagation in space and time. But as we know from our experience that there is probably no place that is devoid of any medium, or there is nothing like a perfect vacuum anywhere. So, whenever there is a propagating wave that propagates from one place to another, it encounters the presence of a medium, however thin or however dense it may be. And this introduction of a medium defines another variable to describe this intervening object, that is the center of mass velocity of the medium. If the medium is at rest, then this quantity that we call the 4 velocity of the medium has its temporal component to be only finite and spatial components can be 0. But if it is in motion, we can have these two things both non-zero. But what we can do is by a Lorentz boost go to a frame where this particular variable is same as that of a medium at rest in a particular frame of reference. Now, if we have 4 velocity vector u mu defined on a moving frame or on a rest frame, its discrete properties should remain unaffected whether we consider the moving frame or the rest frame. Okay? And if that is the case, we might as well find if their transformation properties in a rest frame, because that's simpler, and generalized the transformation property for any frame. The definition of this thing that goes by the name center of mass 4 velocity is defined in terms of a parameter that's called usually proper time interval. So, u mu is dx mu by d tau, which is a proper time interval, and you can see that the 0th component of that is equal to 1 over square root of 1 minus dx by dt whole square. Dx by dt is usually what is called as the velocity. So, if the velocity is equal to 0, the u0 component at rest is equal to 1, and the other components automatically from the definition that we have given in the second line of the slide turn out to be 0. The other properties of u mu, like under parity transformation, it can't be derived from the property of the medium at rest, and if it is done appropriately, the way we have done for other coordinates, then you can see that under parity contravariant u mu goes to covariant u mu, and the suspense field discovery is under charge conjugation. However, that is not the case. It picks up a sign. So, that surprise needs to be brought out to you properly, and we try to do that by looking into this particular problem from a different angle that gets more focused on itself when one uses the language of thermal field theory. In thermal field theory, when you talk of the Green's function or propagation of a signal from one place to another, this Green functions, they have in their medium dependent part a multiplicative factor which is called as a statistical factor, and these statistical factors depend on step functions and the corresponding Fermi-Dirac distribution function. The Fermi-Dirac distribution, if they are replaced with the corresponding Bose-Einstein distribution function, does not affect our conclusion as long as we have finite charge density for either the bosonic system or the fermionic system. What matters here is the change of sign of the chemical potential mu under charge conjugation. So, under charge conjugation, if we have chemical potential sign changed and to conform itself to its original definition, then in the distribution function, we must have the change accompanied by in the velocity 4 vector u. So, that takes care of the distribution part of the statistical factor, and what remains is we have to make the similar changes on the step functions so that under charge conjugation the statistical factor does not change or it remains the same. And this is by inspection follows from the fact that under u going to minus u and mu going to minus u, eta t of as a statistical factor of p dot u remains the same. In other words, eta t of p dot u should be equal to eta statistical or of minus p dot u, and that is obtained at the identification that under charge conjugation the velocity 4 vector also should change. So, by now we have a control or we have understanding how these variables those appear in a description of a wave that is propagating in a medium. They change their form if we boost the system, if we rotate the system, or we take charge conjugate the system or something like those. Thank you.